Hello again. In this session, it's a quickie. We're going to talk about anisotropy. There are coordinate transformations that are made use of for anisotropy in the plane of a domain, and we'll talk about that. And that leads to an equivalent isotropic domain where we can superposition and do all the things we do with analytic elements. I'll talk about the different inputs that you need for anisotropic domains. And I'll show you one example model and how the anisotropy affects head contours, path lines, and so on. Anaqsim allows very general anisotropy capabilities. You can have anisotropy in the plane of the domain that you're modeling, and you can have anisotropy in the normal to that plane. So in a multi-layer model, you can have a vertical conductivity that is different than the horizontal conductivities. The anisotropy in the plane of a domain makes use of a coordinate transformation that's been around for about 100 years. I have some references at the end, the last slide, to that. Muscat did a paper in the 1930s where he outlined this coordinate transformation that's very clever and useful. And here in this sketch, I'm showing an Anaqsim model with 3 domains, and then with the subdomain method, those 3 domains are pulled apart. And if there's anisotropy in the plane of these domains, you can do coordinate transformations on each of them, and they can be different for each of them, to end up with domain models that are stretched in the direction of the lower of the 2 conductivities or transmissivities. So for example, this green domain in the real coordinates looks like this, but its conductivity is higher in this direction, hence the longer arrow, compared to that direction. So we stretch this in the lower conductivity direction, and what was that shape is now this shape in an equivalent isotropic domain. Same thing happens for the blue domain, which is more conductive this way than this way, so we stretch it in that low conductivity direction and get a shape like this, and that's an equivalent isotropic domain where we can superimpose analytic elements and use the AEM like we do in isotropic situations. And likewise, the third yellow domain transforms from this shape in the real world to this in the equivalent isotropic setting, and it's been stretched this way, which is the lower conductivity direction. This slide explains how that coordinate transformation works. The first equation here is the left side of our general equation in the case where we've got anisotropy. And just for simplicity, we've lined up the principal directions of conductivity or transmissivity parallel to the x and y directions. So we have transmissivity in the x direction, which is different than in the y direction here. So our coordinate transformation is this second line where capital X is defined and capital Y are defined in terms of the real coordinates little x and little y. Y is unchanged in this particular formulation of it. There are multiple ways to skin this cat, but this is how I've done it. You multiply the x coordinate, the real x coordinate, by the square root of the ratio of the y transmissivity to the x transmissivity to get a new transformed capital X, capital Y coordinate system. And in that coordinate system, there's an equivalent isotropic transmissivity, which is the square root of the product of the 2 transmissivities. And T sub E is the equivalent isotropic transmissivity. Now, if you combine these top 3 equations, you can get the left side of our general equation now written in terms of the capital X, capital Y coordinates. And it works out to be an equivalent isotropic system where we now only have T sub e in both the two terms here instead of differing values like we had originally. And it's this coordinate transformation that allows that. I won't go through all the algebra that gets you to this step, but trust me, it does. So once we've got this, we can define a aquifer discharge potential such that these equations are true, define it in terms of head and the capital X, capital Y coordinates. So these equations are true, and then we combine this equation and this equation to get our new left side of the general equation, which is the Laplacian of this discharge potential, which is just what we want, because now we can go back to using our typical analytic elements for wells, lines, and areas. Let's look at a couple of example coordinate transformations for this anisotropy in the plane of the domain. Here's the equation from the previous slide for the new capital X, comma Y coordinates in terms of the real coordinates lowercase x, comma y. So the y coordinates are unchanged, but the x coordinates scale up or down by this factor, the square root of the ratio of the transmissivities or hydraulic conductivities, because they're essentially the same ratio. So in this first one, the blue domain in the real x, comma y lowercase coordinates looks like this. But when we go through the transformation, it becomes like this. And these arrows show you that the t in the x direction is quite a bit larger than in the y direction, which means that this factor becomes less than 1, which means that the capital X is shorter than the lowercase x. So we look at this. The y is unchanged, so this distance is equal to this distance across the domain that way. But this distance here is the x direction distance has become shorter when we go to the capital X because this factor is less than 1. Here is the same thing, but now with a flipped anisotropy so that the x direction transmissivity is less than the y direction transmissivity. When you look at this factor, in that case, it is going to be larger than 1 because ty is greater than tx, and that means capital X is larger than x. So again, the y direction is unchanged from the original to the transformed, but the x direction, capital X, is larger than x. You may think that there's some adjustment needing to be done to lengths and areas, which is true because in the equivalent isotropic domains here, the lengths and areas differ from what they were up here in the untransformed real world. But you don't really have to worry about any of that. That's all taken care of under the hood by Anaqsim. All you need to do is specify the hydraulic conductivities, and if they're anisotropic, the orientation of that anisotropy in your domain input. Anaqsim takes care of all the rest. Here's a quick discussion of the input that you need to put in for conductivities when you want anisotropy. So in the plane of the domain, there are two conductivities defined, K1 and K2, and these are the principal directions. One of these two is the largest and the other is the smallest, and it can be either way. K3 is normal to the plane of the domain, usually vertical in a multi-layer model with domains, the plane of the domains being horizontal. If you want anisotropy in the plane of the domain, have K1 unequal to K2. For vertical anisotropy in a multi-level model, have K3 different from K1 and K2. And the anisotropy direction and ratio can be different from one domain to another, even in the same model level. That's something that was not possible in other AEM programs. In fact, I think anisotropy wasn't something any of the other authors built in. Here's an example of inputs. The first two lines, these are from the domain input tables. We've got K1, and I say horizontal, assuming that we're using this in the typical mode. You can also flip it on end and do vertical plane modeling, which is the subject of a later video in this series. But anyway, the first line here, we have K1 at 2.5, K2 at 2.5, and the K3s specified the same way. So this one is isotropic all around. Another way to write that is the second line, where for K2 you just say equals K1, and same for K3s here. And that's shorthand, and it's kind of handy because sometimes it's just less work to only change one number, and it's also less work for parameter estimation programs to just change one number or float one number. The second two lines are also equivalent to one another, but have anisotropy. This first one, K2, is 1/5 of what K1 is, and another way to write that is equals K1 times 0.02. And K3 is 1/10 of K1, and here's another way to write that. The reason for selecting K3 vertical top half and bottom half is to give you the possibility of simulating an aquitard implicitly. If there's an aquitard just above your aquifer domain and you want to incorporate the vertical resistance of that aquitard but not incorporate the layer directly, you can adjust the K3 of the top half. And also there are other cases where you might just assume there's a different K3 on the top and bottom half if the stratigraphy warrants thinking that way. Here's an example Anaqsim model showing anisotropy in the plane of the domain in a couple of ways. We have two different domains here. Most of the area is this one, which is anisotropic with the high conductivity direction oriented like this, 30 degrees north of the x-axis, or counterclockwise from the x-axis, and a ratio of 3:1. The higher direction is like this, the lower direction perpendicular to that. Down here, this is an interdomain boundary, and on this side of it is another domain that in general is more conductive than this area out here, and its anisotropy is different. There's a 5:1 ratio where the axis is 45 degrees clockwise from the x-axis, so south 45 degrees east, say, parallel to that, is 5 times more conductive than perpendicular to it, like that. And we also have two pumping wells, one there, and you can see that the contours around the pumping wells are not circular like it would be with isotropic, and in fact they become ellipses with aspect ratios equal to the square root of the ratio, in this case square root of 5, different between this direction and that direction. This one, it's a square root of 3 difference this direction versus that. We also have an impermeable barrier here made with a normal flux specified internal boundary with the normal flux set to 0. And we have path lines here in the model to demonstrate that when you have anisotropy, path lines in general are not perpendicular to head contours like they are in an isotropic situation. And you can see that almost everywhere in this model. Here are some references on this anisotropy topic. This is Muscat's old one that outlines the square root coordinate transformation, and that's repeated in this Baron-Dagan article here. And my article here in the middle was a special solution that is implemented in Anaqsim for a well in an anisotropic domain, which is relatively simple until you get close to the pumping well. Then you don't want ellipses for your head contours, because that wouldn't conform to the circular boundary of the well itself. And I use a conformal mapping to get that boundary condition met very accurately at a well.